Hello everyone. So this is a question from JEE Advanced 2025 paper 2. The solubility of barium iodate in an aqueous solution prepared by mixing 200 ml of 0.01 molar barium nitrate with 100 ml of 0.1 molar sodium iodate is X into 10 to the power minus 6 mole decimeter to the power minus 3. The value of X is, okay. Use solubility product constant Ksp of barium iodate as 1.58 into 10 power minus 9. The chapters involved is ionic equilibrium. Now, um, there are few words, that is, for example, solubility and solubility product. These are the two words which are very important to us. So, to start with, let's say that we have a sparingly soluble salt. The meaning of sparingly soluble is something, I mean, when we talk about a sparingly soluble salt, that means a salt with very small amount of solubility. Okay, so sparingly soluble salt means salt with small amount of solubility. For example, AgCl. So if a sparingly soluble salt is stirred with water, only a small amount of it goes into the solution. Makes sense because it is a salt with very small amount of solubility. So a very small amount of it goes into the solution, and most of the salt it will remain undissolved, right? Because it is sparingly soluble. Whatever little amount of salt dissolves, it gets completely dissociated into ions, right? So what I'm trying to say is, if you have a salt with very small amount of solubility, whatever little amount that goes into the solution, it completely dissociates into ions. So when a sparingly soluble salt is added to water, there is a dynamic equilibrium between undissolved solid salt and the ions with which it furnishes in solution. Very important. When sparingly soluble salt is added to water, there is dynamic equilibrium between undissolved solid salt and the ions which it furnishes in solution. That is, if we want to represent it through a diagram, let's say we have a container and we have water in it, and let's say we added some amount of salt. So what will happen, most majority of the salt, it will remain undissociated. Whatever amount has gone inside, it will dissociate into ions, and there will be equilibrium between the undissociated or left salt and the ions that it has furnished in the solution, which can be represented by a equation or a reaction form, that is AgCl solid, that is the undissolved salt, is in equilibrium with Ag plus the ions that it has furnished in the solution, right? And at equilibrium, we know the rate at which this solid AgCl dissolves, the forward reaction, will be equal to the rate of the opposite process of precipitation of these two guys to form the salt AgCl, solid salt AgCl. So because of that, the amount of undissolved salt does not change. Very important. Okay. So whatever amount of salt got dissolved into the solution, so obviously we have certain amount of undissolved salt left. The amount of that is not going to change because the rate has become equal now, forward and backward. Okay. So here the forward reaction is dissolution, the backward reaction is precipitation. Okay. So then we can apply law of chemical equilibrium to this particular reaction. So we will get K is equal to Ag plus Cl minus divided by AgCl, right? And we know that concentration of undissociated solid is constant because it has reached equilibrium. So after equilibrium, the concentration does not change. So we can write concentration of undissociated solid is equal to constant. So therefore, we can write KSP. So this K then becomes KSP, which is our solubility product. So that is equal to Ag plus concentration of Ag plus ions in the solution into the concentration of Cl minus ions in the solution. So that's the meaning of solubility product. Okay. So it is basically the equilibrium constant when for a saturated solution. Whenever we have formed a saturated solution, what is saturated solution? A solution in which we have added the maximum possible amount of solute. Okay, so one more example to calculate KSP will be, for example, let's say we have calcium phosphate, which is Ca3PO4 twice. So this guy, when whatever amount of it dissociates, it will form calcium plus 2, 3 of them, and 2 PO4 phosphate ions. So whatever amount of calcium phosphate is being left and whatever has dissociated, both are in equilibrium now. Okay, so the KSP here will be obviously concentration of Ca plus 2 ion to the power its molar coefficient, stoichiometric coefficient is 3. Then concentration of PO4 minus 3 to the power its stoichiometric coefficient 2, right? And one more important point that you should remember is the solubility product of a salt, that is KSP, is a constant at constant temperature. Very important. KSP is a constant at constant temperature. Now let's talk about solubility. It is the maximum amount of a substance, that is the solute, that can dissolve in a specific amount of solvent at a given temperature and pressure to form a stable solution. Very important. So solubility is maximum amount of a substance, that is solute, that can dissolve in a specific amount of solvent at a given temperature and pressure to form a stable solution. Okay, it is often measured in moles per liter or molar. So its unit is moles per liter, or it is also molar. The relation between solubility in moles per liter and solubility product, that is KSP, depends upon the nature of the salt. Okay, very important. So we'll see that how. So in our case, salt is barium iodate. Okay, so barium valency plus 2, iodate is IO3 minus 1, cross multiply. So our salt is BaIO3 twice. Okay, so this guy will dissociate into Ba plus 2 plus 2IO3 minus ion, right? According to stoichiometry or stoichiometric coefficients, if the solubility of BaIO3 twice, that is barium iodate, is S molar, then the amount of Ba plus 2 formed will be also S molar, and the amount or the concentration of IO minus 3 will be 2S molar. That is due to stoichiometry, because you can see each BaIO3 twice produces one Ba plus 2 and 2 IO3 minus. So therefore, if the solubility of barium iodate is S, the concentration of Ba plus 2 formed will also be S, and the concentration of IO3 minus or the iodate ion will be 2S because of the stoichiometry. So therefore, KSP will be obviously the product of the concentration of these ions raised to the power of their stoichiometric coefficient. So it will be KSP will be Ba plus 2 into IO3 minus to the power 2. right? The concentration of Ba plus 2 is S, and the concentration of IO3 minus is 2S. So therefore, Ksp will be S into 2S whole square. So therefore, it is going to be 4S cube, right? So now coming back to our question, to prepare barium iodate, we are mixing 200 ml of 0.01 m barium nitrate, that is BaNO3 twice, with 100 ml of 0.1 m NaIO3, which is sodium iodate. So we have 200 ml of 0.01 m barium nitrate with 100 ml of 0.1 m NaIO3, right? And we know that molarity is equal to number of moles of solute divided by volume of the solution in liters. Cool. So therefore, we can calculate the number of moles of BaNO3 twice, which will be present in this solution. We can also calculate the number of moles of NaIO3, which will be present in this solution, right? So in this case, it will be 0.01 molarity. So you can see number of moles is molarity into the volume in liters. Okay. So it will be 0.01 into 200 by 1000, that is 0.002. So this is the number of moles of BaNO3 twice. The number of moles of NaIO3 will be 0.1 into 100 by 1000, which is 0.01. So this is the number of moles of NaIO3. Okay. So writing the balanced chemical equation between them whenever they react with each other, so we get BaNO3 twice plus 2 moles of NaIO3 is giving us BaIO3 twice plus 2 NaNO3. So this is the balanced chemical equation, right? And it is given to us that we have 0.002 moles of barium nitrate and 0.01 moles of sodium iodate, right? Okay. According to stoichiometry, can you see 1 mole of barium nitrate needs 2 moles of sodium iodate, right? So therefore, let's find out how much would 0.002 moles of barium nitrate require. So we can write 1 mole, according to stoichiometry, 1 mole of BaNO3 twice needs 2 moles of NaIO3, right? So therefore, 0.002 moles of BaNO3 twice, that is barium nitrate, will require how much? 0.004 moles of NaIO3, right? In the reaction, we have 0.01 moles of NaIO3, which is more than the required amount, right? So therefore, this guy NaIO3 is the excess reagent, and BaNO3 twice, barium nitrate, is the limiting reagent. So therefore, whatever amount of product will be formed will depend upon, these two guys will depend upon the limiting reagent, that is barium nitrate. Okay, so let's write it down that according to stoichiometry, we have 0.002 would actually need 0.004. Okay, and you can see 1 mole of BaNO3 twice produces 1 mole of BaIO3 twice. So therefore 0.002 moles of BaNO3 twice will produce 0.002 moles of BaIO3 twice. So therefore I will write 0.002. Again, you can see 1 mole of BaNO3 twice produces 2 moles of NaNO3. So therefore 0.002 moles of BaNO3 twice will produce the double amount, 0.004. Okay, so 0.004. So therefore, after the reaction, we will be having 0.002 moles of BaIO3 twice and 0.004 moles of NaNO3. And remember, According to stoichiometry, 0.002 needs 0.004, but this much is given to us, right? Actual requirement is this, but this much is present. So therefore 0.01 minus 0.004 amount of NaIO3 will still be left. Okay, so I will write down 0.01 NaIO3 is given. According to stoichiometry, 0.004 NaIO3 will be consumed. Therefore, 0.01 minus 0.004 NaIO3 sodium iodide will be left, which is 0.006, right? So therefore, after the reaction, we will be left with 0.006 moles of NaIO3, right? All of the barium nitrate would have consumed because this is the limiting reagent. So therefore, here it will be 0. And in the products, we will be getting 0.002 moles of barium iodate and 0.004 moles of sodium nitrate. Okay. So after the reaction, so we started with 0.002 moles of barium nitrate and 0.01 moles of sodium iodate. And after the reaction, we are left with 0 moles of barium nitrate because it is the limiting reagent. We have 0.006 moles of sodium nitrate left. We have 0.002 moles of barium iodate. Sorry, this is sodium iodate, and we have 0.004 moles of sodium nitrate. Okay, cool. So rewriting our solubility equation, if you remember, so I'm erasing this. So rewriting our solubility equation, that was BaIO3 twice, giving us Ba plus 2 and 2IO3 minus. Okay, remember it was S and 2S, right? So we can say that S moles per liter or S molar of BiO3 twice in the solution gives S moles. So S moles per liter of BiO3 twice in the solution gives S moles per liter of Ba plus 2 ion and 2S moles per liter of IO3 minus ion, right? But here there is a catch. The catch is these IO3 minus ions are also produced from the left sodium iodate. Remember, this much amount of sodium iodate is left after the reaction. So let's calculate the concentration of this much amount of sodium iodate, that is concentration of 0.006 moles left NaIO3 will be equal to, obviously concentration is number of moles, 0.006 divided by volume. Do you remember the volume was 200 ml of barium nitrate and 100 ml of sodium iodate. So therefore the total volume will be 300. So 0.006 divided by 300 into 1000. So that is going to be 0.02 moles per liter or molar, right? And we know that NaIO3 dissociates completely. So NaIO3 will dissociate completely into Na plus and IO3 minus. So therefore, if we have 0.02 moles per liter of NaIO3, we will have 0.02 moles per liter of IO3 minus ion. So therefore, IO3 minus concentration, IO3 minus concentration will be also 0.02 molar, right? So therefore, coming back to our OG equation, so concentration of Ba plus 2 is still S, no doubt about that. So concentration of Ba plus 2 is still S, but the concentration of IO3 minus won't be just 2S because remember there is left over NaIO3. So it will be 2S plus 0.02. So therefore it will be 2S plus 0.02. Now This 2s is very, very small compared to this 0.02. So therefore we can ignore this 2s. So therefore the concentration of IO3 minus is actually 0.02, right? And we know that Ksp of BaIO3 twice will be equal to the concentration of Ba plus 2 ion and concentration of IO3 minus to the power square, right? And Ksp is given to us in the question that it is 1.58 into 10 to the power minus 9, and Ba plus 2 we know it is S, and IO3 minus concentration we just calculated it is 0.02, right? So 0.02 whole square. So therefore S will be equal to 1.58 into 10 to the power minus 9 divided by 0.02 whole square. When you do this calculation, you will get 3950 into 10 to the power minus 9. But our answer should be something into the form of 10 power minus 6. So I will multiply this by 10 power minus 6 and divide by 10 power minus 6. So then we will get 10 power minus 9 and 10 power minus 6 as 10 power minus 3. So this whole thing becomes 3950 into 10 to the power minus 3 into 10 to the power minus 6, and this is 3.95 into 10 to the power minus 6. So therefore X is, or the solubility is 3.95 into 10 to the power minus 6, where this value is our X. Okay, so answer will be 3.95. 3.95. Okay.